Assalamu alaikum everyone. Welcome to our new course, new lecture. This is actually continuation of the previous lecture. So what we have learned in the previous lecture is prefix-free coding. We all have seen that we need a prefix-free source code so that the code can be decoded exactly or precisely with error-free, right? So today we will study binary tree representation of code. This is actually our, so now by binary code representation, it will actually help us to find or to generate prefix free codes. So let's see. So why we need binary tree representation? For designing and decoding of codes. Here there is an example given for of a code word S0, S1, S2 and S3. So we have seen that this S0, S2, S3 and S4, they 0, 1, 2 and 3, these are not a fixed length code. They are variable length code. Okay. So, and we can see that, for example, this is actually prefix S in S2 is actually prefix of S3. Okay. We can easily see it from the list, but yet if we design a binary tree or we convert or represent it to the equivalent binary tree, this is actually our equivalent binary tree. So how it starts? We actually starts from here. Okay, so the upper length goes for 1, the lower length goes for 0. Okay, so 1 and 0. Okay, now if we go further 0, then it will become 0, 0. So who is 0, 0? This is 0, 0, right? S1. That's why it's S1. Now from 1, if you go further 1, then it's 1, 1, right? So 1, 1, which is actually S2. In our cases, S2. This is, you see, S2. If you go from here 0, then 1, 1, 0 is this code S3. S3. Okay, this is how we and also 1 and 0, this is S0, 1 and 0, S0. So here we can see that if you want to have S3, you have to pass through S1, right? Means actually S1 is the S2. So S2 is the ancestor of the S3. If some code is ancestor of other code, means they are not prefix free. Or in other word, we can say S2 lies along the path of S3. If you want to, like, if I go from here, then S2 lies along the path of S3. Means actually S2 is the prefix of S3. S2 is the prefix of S3. That's actually we are saying here. Of course, by the binary tree representation, you can easily see if some codes are prefix free or not. Here is another example. Okay, so same way that you have like upper hand will be the 1 and lower one will be the 0. Okay, so if you go for 1 again, then it becomes 0, 1, right? So 0, 1 is S1, S1. So 0, 0 is okay, 0, 0, 1 is S2, 0, 0, 1 is S2. So 0, 0, 0 is S3, 0, 0, 0 is S3. You see here, no code word is ancestor of the any other code word. Means actually it's become a prefix free code. And all the codes are in the leaf node. That's the reason they becomes in the leaf. If it's a tree, then they are in the leaf. Nodes are in the leaf. That's why they are actually prefix free. You see, this code this code is equivalently represented by the binary tree, which actually gives you a visualizations for understanding whether some codes are prefix free or not, or they have any ancestor, right? So by these two example, we actually see if there is a prefix free or not. Okay. Okay. Now the same example, previous example, this example. Let's see. This example is actually again represented here, just in a nice diagram. Okay. Now here, this is the same one, and by the black dot, okay, means actually this one, these are the missing one, means actually they are not existing. Okay, so I wrote it like, if they would be as existing, how would they look like? So if they would be existing, then this would be the complete tree, but there is no nodes, no data here, right? No code here. But if there would be a code, this would be the this will be the complete tree. Here, this is the level L0. L0 is a, if it's one, here you see I have divided it in different level. So level 1, level 2, level 3, or you can say depth 1, depth 2, depth 3. Like from the root of the tree is going, so this here all are equivalent, 1, then is 2, so they are level 2, is 3, so they are level 3 or depth 3, whatever you say. So here in this example we can see that binary tree has, this binary tree, particular binary tree has a depth of 3, which we actually is denoted by L max. Okay, L max is the maximum depth of the binary tree. Okay, so number of nodes eliminated at level 3. At level 3 means here how many nodes will be eliminated is expressed by this equation, 2 to the power L max by minus Li. Li is the value. For example, our case is Li is equal to 1. So 2 to the power L max is 3, minus 1 to the power 2, 4. So number of nodes eliminated at level 3 will be 4. We can see this one, this one, this one, and this one, they are eliminated at node 3. These nodes are not came into this these nodes didn't came into consideration. That's actually we are trying to say. Okay, means actually by eliminating this number of nodes, by eliminating this number of nodes, we make the code as a prefix free. Okay, means actually for prefix, to make a code word prefix free, you need to eliminate it some, because which will be having ancestor, same ancestor, just to remove that. Okay, so this is the way. Now here L max is nothing but the maximum number of code word. Okay, which is 2 to the power 3, which is 8. How many code word is possible here? You see 1. Okay, we see 1, 2, 3, 4, 5, 6, and here this data is missing. This means this is not existing. If it would have been existing, there will be another 2 node. So 8. That's actually the value of 8 L max. Okay. So 3 is the depth. So in a prefix free code, each code word for SI is a our alphabets is 1, 2, 3, 4, 5. All this corresponds to the 2 to the power L minus M. This distinct code word at depth L max of the binary tree. So in plain word, for a prefix free code, this represents a maximum this number of distinct code with a depth of this L max. Okay, for our cases, this will be our distinct code, this number of distinct code, and this will be our maximum length. Okay, so we can write that, we can write this, we can write all the code here, I to the power 0 to m minus 1 2 to the power L max minus Li will be definitely less than 2 to the power L max, because 2 to the power L max, this is the maximum number of node or code word possible. Here you see, here L max is the 8, but you have to eliminate, if you eliminate to make it prefix free, this is actually your number of, right, code word. This is the maximum, and after elimination you get this one, so this will be definitely less than, this is, that's why it's a less than to the power L max. Lmax is nothing but the maximum number of nodes in the binary tree, right? So if we take 2 to the power Lmax separate and cross the Lmax, we find this one. So this one we actually rewrite here that okay, this equation that 2 to the minus Li where I equal to 0 to m minus 1 is less than equal to 1. This is an inequality. This inequality is called Kraft inequality. Means actually, in plain words, it says that if you observe or if you apply the Kraft inequality, or if you can deduce or derive this condition of the Kraft inequality, you will end up the number of code word who will be prefix free. So this is the condition. Kraft inequality is a condition to achieve a prefix free code for various distinct S0, S1, S2 for different level L0, L0 up to this value or this code word length. Okay. So in plain English, if Li satisfies the condition above, there exists a prefix free code with code length of Li, which actually we say this is actually done by the Kraft inequality. Okay. So we know that okay, if we have a binary tree, then it will be easier for understanding to actually find the prefix free codes by fulfilling the Kraft inequality condition. Okay. So now what should be the average code length? Means actually we need to characterize the minimum possible average code length. We need to characterize the minimum possible average code length for whom? For the source signal X, which actually belongs to S, which have the these alphabets, right? We actually write we have written this equation before. So now let's see in our previous class what are the other formulas we find. We found that the probability of the SI is denoted by the PI, which is actually the length of the code word I be the Li. Here the Li is the length of the code word. Also, we find in our previous class that the average code length is this M0 Pi Li equal to L. Remember, we will use this equation. And also, just now with Kraft inequality, we find this equation. Though means actually uh, this equation we will be using in our next section. Okay. So here we define a quantity Qi. So Qi is defined by these two quantity. Here the aim is to make Qi is a positive value. When Qi will be a positive value, if the numerator and the denominator both becomes a positive value, then Qi is automatically becomes a negative value. Also the also furthermore we find this. You see here 2 to the power Li and 2 to the power Lj minus Li and minus Lj. Here minus Lj, this part is J contains the whole series because J goes from 0 to m minus 1 where I is also a component. Okay. So if this happens, means actually this one is actually combination of all J from 0 to m minus 1 where I is also a component. If this is the case, then this amount is definitely greater than this amount, because this part is a component of this whole summation. It's actually a part of this one, right? I is a part of J. J is a series, whole series 0 to m minus 1, where I is a, for example, J is from 0 to m minus 1, where I is a component. Means actually the summation of whole series will be definitely greater than the only this component value, right? That's we are writing here. Okay. So 2 to the power minus I, actually this one to the minus I. This part is now becomes on the other side, which actually, okay, so I can rewrite it. So how it looks like 2 to the power. So this part I am writing 2 to the power minus L I, like this one. So here 1 remains and this part goes here. J equal to 0 to m minus 1 to the power minus L j. That's actually I am writing here. Where this part we also know this is a q1. Here from here we know this is a q quantity, means actually qi is actually less than 1. So we find it that okay, q value has to be from here. We find the range of qi. We find the range of qi. Qi has to be greater than 0 and it has to be less than 1. Okay, by this and this we actually find the range of qi. Okay. Okay. So so summation of I equal to 0 to m minus 1 qi, we can rewrite it. We know the qi value. Qi value is this one, which is actually this part, and this summation, this is the one. Okay, so we actually putting it into the numerator, this easily goes there. So which is actually this part, and the lower one, which actually equals to 1, definitely. Now we find two conditions. We find that okay, this is the limit of the qi and summation of qi is 1. Okay, this will actually give us a fantastic idea about the nature of qi. It gives us that okay, qi is a probability distribution, is a probability distribution. Okay, here we will, because we just find a probability distribution, to solve it we will introduce a theorem or divergence theorem, which is called Kullback-Leibler divergence. We can shortly call it KL divergence. Okay, so Kullback-Leibler divergence. What is a Kullback-Leibler divergence? What is actually says? So it's actually a mathematical operation where we, so Kullback-Leibler divergence actually gives us the probability distribution in two different distribution, like one reference to another one. So it actually gives a measure of how one probability distribution is different from the second on one or the reference probability distribution. Means if you have two probability distribution p0, p1, p2 up to pm l minus 1 or q0, so by Kullback-Leibler distribution we will find how one probability distribution is different from another one. That's one. Okay, so this is actually a generic formula. So Kullback-Leibler distribution actually defined by the D. So here actually you have two distribution, fx and gx, for example. So this is how it will be expressed at. Okay, minus infinity means actually integration of fx log 2 fx by gx dx. So this is actually a general formula. We will apply this formula to our equation. So KL divergence for the probability mass function. Okay, here we were talking about probability distribution function, but because our series, you see this series, this series, this one, this is actually a this is a discrete series. That's why instead of calling it probability distribution function, we call it probability mass function. Same thing for a distributed for a discrete function, probability distribution function is actually treated as a probability mass function. Okay, so this is the formula. So KL distribution for P and Q is greater than 0. So we put the this one equivalent formula, this one, where we have integration. You see here there was integration. So this integration, because we have probability mass function, that's why integration will be replaced by a summation. But then fx, which is pi log 2 pi by qi. So pi by qi greater than 0. Okay, so here the pi part, this is the pi, and this is a 1 by qi. Okay, so 1 by qi is this one. Just divide the log part, because we know log multiplication is nothing but the summation, right? That's we are writing. So now we give it as a name, this part. We will deal it with a letter minus hs. Okay, we will try to solve this part now. Okay, we will try to solve this part. For here, again recall this qi. We know this was our qi value, right? So 1 by qi will be like flipping this. Okay, so log 2 qi, you see we are trying to achieve this part. So log 2 1 by qi is nothing but the log 2 of this part, right? This part, that's we write here, log 2 this part. From Kraft inequality, we know that this is the condition, Kraft inequality. If this is the case, means in Kraft inequality, 2 to the power L j, where j equal to 0, m minus 1, if it is less than 1, the log 2 of this version will be less than 0. It will be a negative value actually. That's actually we know definitely. Okay, so log 2 this part, the log 2 mj this part, we will actually try to apply it here. Okay, now log 2 1 by q, log 2 1 by q, this part we actually trying to derive it. Okay, here we can say that, okay, this is actually nothing but these two, so this is divided log 2, so we can divide is nothing but a we know it, log of a by b is nothing but the log a minus log b, right? Based on the base, if it's 2 then 2 log 2 2, right? We know it. So this is actually same thing I did here, because you see here this was minus sorry, this part was minus, you see, minus L I. When you took it out, it will be, sorry, when you took it out, it will be that minus is gone here, right? It's no more here. Okay, and the other part. Okay, now 2 to the power 2, this is equal to 1, so if I have Li minus, okay, so this is f psi. Now this one, we know that this will be a negative value, right? From the previous equation, this will be log 2 of this value. These are the negative value. Okay, so it's a negative value. Negative, give it a name, f psi. Okay, now we will actually put up, insert this equation to our original equation, which is actually this one, equation 1, the complete equation. Okay, so we are putting this value. So this was, we already give it a name, and these are the value Li minus 1, which is actually here. So we actually again take it out, that P Li, this part is nothing but this part, right? Pli. So this part actually goes here, where we lose the negative sign, and also this part for f psi, which is also lose the, if it goes to the opposite side, there is no negative, right? Okay, now we already know that this amount is nothing but the L, and this is this part, this is a constant, so which is a constant, we can actually avoid it. Now we find that L is the greater than the hx. What is hx here? Hx is nothing but the entropy. So here we find the boundary condition. The fundamental boundary on average code length for a given source for any prefix free code is the fundamental limit. By from here we find the fundamental limit of this code. We can also say this entropy is the lowest boundary for this average code length. This entropy hx is the lowest boundary for the, okay, we can write that entropy is the lower or lowest boundary. Okay, lower boundary or lower bound for average code length. Same thing, eh? Whatever it means is also means actually we have a fundamental boundary which actually we were looking so far for this average code length, that we want to characterize the minimum possible average code length. How we find? If we know the lowest boundary, actually this is related to the entropy. Okay, for what? For a prefix free codes. Okay, so we will end up here.